Hello and welcome. My name is Kevin Broten de Carvalho, and I'm one of the PhD students here in the Federal University of Viçosa, as well as one of the students of the Robotics Specialization Nucleus, which is NERO. I'm here to present you one of our papers. It was published on the International Journal of Advanced Manufacturing Technology. So let's begin. This paper is all about human-robot interaction. So first of all, we must define what it is. And there are many definitions, but this is one of them that I'm most fond of, that says, human-robot interaction is a field of study dedicated to understand, design, and evaluate robotic systems for use by or with humans. And this interaction is highly modified, highly influenced by the nature of the communication, which can be remote communication when you are far away from the robot. You can teleoperate it, or you can just receive feedback on the control room. This is remote communication. And we will have also proximate communication, which is when you're at least in the same room as the robot. And they will modify the interaction a lot. And there are also different means for communication. And it can be by voice activation, like you do with your cell phone when you ask it to search something on Google, play a song on Spotify. There is also peripheral communication. If you want to send a robot to a specific place in a map, it's easier to just pinpoint on the map using a peripheral, just like a touchscreen or something like that, instead of explaining by voice. But the centerpiece of this paper is all about gesture communication. Okay, so we will be working with this. When it comes to applications, we have different types of them for remote communication and for proximate communication. The first example is for search and rescue scenarios, which is kind of a little bit of both of them, because you might be teleoperating the robot because you don't want to go in a place that is not safe for you. We can also say about military applications, such as Fair Lady. She will be teleoperating this robot as if she's on a bomb squad. So the robot will do all the close work while she's safe, far away from the possible bomb scenario. And one of the main motivations of this work is surveillance and inspection situations, where you can see a ground robot as well as an aerial one working together to surveil and inspect a specific area. When it comes to proximate communication, we could say that we have proximate communication when there's a robot operating in somewhere where you have constant human presence. So each time it communicates with them, it'll be proximate communication. And we can also have a cooperative scenario where the robot will directly help the human for a specific task. And when it comes to tasks, let's say if you use multiple agents, you will be able to at least do the task more efficiently, or at least with more flexibility, right? And there are also tasks that it can only be done with multiple agents. For instance, carrying a really heavy sofa, you can't do it by yourself, but you can easily do with the help of one or two friends. So it's really important to talk about robot cooperation. That is why our paper works with multi-robot systems. So when it comes to gesture recognition, first of all, how did we do it? We started working with artificial neural networks, which is a specific and really famous type of supervised learning techniques. And supervised learning techniques, they use label data. You will have label data to teach your neural network how to identify the patterns. So we used as input data from a RGBD sensor, which was the Kinect. And how does it work? It can give you grayscale data or color data, and where each of the pixels will represent intensity of a color. But the depth part of the sensor will give what we have on the right image, where each pixel will represent the distance of what is on the pixel to the sensor, which will highly help to do the gesture recognition. So, first of all, we were worried about data size. Because when it comes to the resolution of the depth image, it will have over 200,000 numbers per frame. And a gesture is not just a single frame, it's a bunch of them. So first of all, instead of using directly the depth information, we used more specific data, which is skeleton data. The Connect will return the 3D coordinates of 25 body joints. So we reduced this from over 200,000 numbers to 75 of them. And furthermore, since all of our gestures use mainly our arms, each arm will have 4 joints on the Connect sensor. So we reduced, instead of using all 25 joints, just 8 of them. So instead of having 75 numbers per frame, we would have only 24. And furthermore, we did some eigenvalue decomposition. So instead of having the first case, which was 200,000 numbers per frame, the whole gesture would be represented by just 8 numbers. So this vastly decreases the amount of information that the neural network will be looking to, so it makes it easier to learn and will make it easier to have a small data set, which is what we use here. Since we're not using data sets found on the internet, we are using our own data set because it will suit better the types of gestures for our applications. So we get the depth data and we transform it to just 8 numbers. Great. So what our gestures were meant to. First, they were meant to operate 2 robots. So it was important to turn on and turn off the robots or take off or land commands. Great. And since we did this work inspired and motivated by surveillance and inspection tasks, we asked the robot to execute predetermined routes or go to the next waypoint. So you can have several waypoints on the area you're surveilling, and you can ask the robot to go to the next one. Or start a cooperation mode or perform emergency mode. Cooperation mode, it's so you can send commands to the robots. Instead of using their spot as reference, it was the other one. So they will work together. And emergency mode, sometimes the environment can change unexpectedly, so you would like a quick response from the robots to do what they're doing, or you ask to do task A, but you change your mind, go to task B. So it's important to go for emergency mode so you can quickly change what the robot is doing. And these are the gestures we use. And I encourage you to pause the video and look for the gestures and see what would they relate to. Something route related, something waypoint related, cooperation mode related, or take off, land, turn on, turn off commands. Well, the answers will be on the pin post and on the video description, so don't peek. For the results, for the gesture results, we did the neural network training and we got over 98% accuracy using tenfold cross-validation, which is a really good result for our application. And to ensure our data set wasn't biased, we did online tests as well, where the computer would ask for a specific command randomly, and the user would have to do it and see how many times the neural network would get it right. So we got over 96.5% accuracy on these tests as well, which is great results. Since this is a application-focused paper as well, we didn't want just to say that our gesture recognition would work. We would like to see the actual robots working on a real-world scenario. We chose real-world scenarios because there's a really big gap from simulation environments to real-world environments. So if we applied for real-world ones, we would already bypass this gap. So we did 3 tests. One with the ground robot and the aerial one to test several different commands. One with 2 UAVs to showcase the predetermined routes commands for each one. And a second one with the ground vehicle and the aerial one for showcasing how it works, the predetermined waypoints. And you can see snapshots from the video. All of the experiment videos will be on the description, so I encourage you to go there and watch the whole video because it really do showcase really well what we are doing. So the first one is the UAV plus the ground vehicle. So in this video we will showcase different commands like cooperation mode, like different routes and the emergency mode as well. The second one, with the two UAVs, we showcase giving different predetermined routes to each one of them. And the third one is the UAV plus the ground vehicle, where we will showcase sending them to specific waypoints. Well, so thank you for watching. This is all. I hope you enjoyed it. Here we have information of the paper, of the journal, as well as institutions that funded us, and as well as YouTube channel information and our GitHub subs. So thank you very much. See you on the next one.